Let's talk about tensors in general here. A tensor of rank 0 is simply your scalar. Think of temperature as your basic example. At each point here, we have a temperature, which is simply a magnitude. A tensor of rank 1 would be your vector. We have two types, the contravariant vector, which we talked about, with the slant going up here with the primes, and the covariant, where the slant with the primes goes this way. You can think of a vector, which is a tensor of rank 1, as having magnitude and direction, as represented by these little arrows, which represent various wind velocities at various places. Here's another example of a vector case where you have arrows showing you the direction where a plus charge would respond, test charge would respond to this plus charge at this origin, and the size is getting shorter means that your strengths are getting weaker as you get farther and farther away. Here's a tensor of rank 2. An example would be the stress tensor, where you have an object and you're applying forces to it, and each of the three major faces here, you can take the face where you have a normal in the z direction, a normal here in, say, the x direction, and a normal in the y direction, and then you have forces applied and on each of the faces, and you can think then as the forces are applied, there's two shear forces and one normal force. So you have 9 things going on, and the other faces would have similar things, but because of the equilibrium equations, the torque, and the translational equilibrium equation, you wouldn't need any more parameters. You basically are covered with these 9 components, which are represented in this little matrix here. That's kind of neat. So a tensor of rank 0, a scalar, a tensor of rank 1, a vector, and a tensor of rank 2, a matrix, a 2 by 2 matrix. In 2 dimensions, the scalar would still be a one-dimensional quantity, one particular component, and then you would have here 2 dimensions, 2 components for the vector, and then the matrix would have 4 components. Not all matrices are tensors. They have to have components that transform according to the formulas that we showed earlier. For example, here is a tensor of rank 1, which is a contravariant case, contravariant tensor of rank 1, and a contravariant tensor of rank 2 would have 2 of these partial derivatives in there with the same kind of arrangement, the primes sloping upward here. So the mn components in the one frame get transformed by this double covariant transformation, contravariant transformation to the contravariant tensor of rank 2 in the prime frame. For the covariant case, you would have the primes slanting downward like this. So this is the covariant transformation, mn components in the one frame, and the ij components in the other frame, the prime frame. A mixed tensor would be one like this, where here you have a tensor of rank 3, since there's 3 partial derivative factors, and you have 2 that transform like the covariant vector, and 1 like the contravariant vector. Therefore, this is a mixed kind of a tensor. It's a tensor of rank 3 with 1 contravariant component and 2 covariant components. See if you can give a 4 dimension, well, for rank 4 case is a better way to put in that, because the dimensions would be independent of this definition. The dimensions refer to when I is going to go through the various cases. If I goes from 1 to 2, that's a 2-dimensional case. If I, j, k, and l go from 1, 2, and 3, that would be a 3-dimensional space. 1, 2, 3, 4 would be a 4-dimensional space. But in all the cases, this would be a mixed tensor of rank 4 with 1 contravariant component and 3 covariant components.